Hello everyone, once again, welcome to our Computer Science 9618 AS and A-Level lecture series. Our topic today focuses on the basic logic gates. Okay, our key discussion, we are going to introduce what are these basic logic gates. We are going to understand and define the functions of NOT gate, AND, OR, NAND, NOR, and XOR gates. Before I begin with the different basic logic gates, let's take a look at the simple applications of logic gates in our everyday life and also in the improvement of the quality of life. Okay, in our homes or at home or even in school, there are a lot of applications of logic gates. First, when we are at home and we usually use our doorbell, that is also an application of what we call this one, logic gates. Okay, even there are some homes or houses, we call it as intelligent houses. They're actually being equipped with many sensors. Again, that is just an example of a we call it a burglar alarm, and that is with the implementation of logic gates. Next up here is that, of course, since the pandemic had begun, okay, there are some many problems that we encountered also, and that the number of flights was reduced. But come to think of it, that there is also what we call an application of logic circuit in the landing gear of our aircraft. Okay, there is an application of logic gates. Also, temperature detector, or there is of course the application of central heating system in an office or a building or an industrial complex, or maybe just your your room. So these are applications of what we call the logic gates. And also on the street, okay, the traffic light control system is based upon the principle of the operation of logic gates. Okay, so this is one of the considered as the best example or application of logic gates. And of course, since we are in the pandemic area or pandemic period, if you can see how these COVID-19, okay, these viruses are being detected, and it also had come to my attention that there is actually an application of logic gates here. Okay, in the detection of the SARS-CoV-2. Okay, so with the use of very important type of gadgets here. Okay, and of course with the inclusion of so many technologies already, but of course, the basics there is actually with the use of logic gates. So as you can see here in the figure, you can see there is a source, there is gate, there is drain. Usually that is transistors, and of course, basic logic gates are considered as there is also a fundamental building blocks of these logic gates. Could be made of transistors or a series of transistors in order for this to be constructed as a logic gate. So even in the medical field, there is actually the application of logic gates. And with these so many examples that I presented, I really would like to give a very good definition here in an ordinary layman's term. And at the same time, of course, it's also based on our the context of our textbook. Usually I define the logic gates as the fundamental building blocks of almost any digital systems. Okay, so when you say building blocks, okay, they comprises, I mean, without this logic gates operation, definitely this is the system would not exist, or digital system would not exist. Okay, logic gates take binary inputs and produce a binary output. Of course, we're going to discuss that later on. And logic gates combined together form a logic circuit. So we're going to demonstrate this in our series of lecture with regards to logic circuits and design. And that is also considered now as the offshoot of combinational logic circuit. All right. There are actually three basic gates. Okay, there should be actually three basic gates that you should know, and of course, there are some other gates, okay, coming from these basic gates that are actually emerged, okay, from these basic gates. The basics are AND, OR, and NOT. And then of course we have some some secondary here modifications, or because of these combinations of the basic logic gates, the AND, OR, and NOT, there is actually an existence of NAND gate. Okay, we have here NAND gate, NOR gate, exclusive OR, we also have what we call XNOR. Okay, now if you notice, there are two sets of symbols here. Okay, the other the symbol set 2 here, set 2 is basing from the American National Standards Institute or from the IEEE, but this is seldom used. What is being commonly used now is with the use of this set 1 symbols here. Okay, set 1 symbols, the one that I'm highlighting right now. Okay, the set 1 symbols. And then during the course, we are just going to make use of this the set 1 symbols here, the most common symbols that we are using, and definitely this is the one that we're going to use whenever we're going to create or implement a logic expression to its equivalent logic circuit diagram. Alright, the first logic gate that we're going to discuss is a very simple gate, and of course I really wanted to focus on the symbol here, but not this one, although I just made a representation. Yeah, you might come across later on with some of the symbols, but definitely the recommended symbol that is being used, class, is this one. Okay, the the common symbols. Usually the inverter, or simply we call it the NOT gate. Okay, from the word alone, inverter, invert. So since it accepts binary values, if this inverter here actually uses only one input, and of course you are going to expect one output. So this area here, this is usually, I call it this one as the truth table or the function table of each gate. Okay, this is the basis. Okay, the truth table is very important. This is the basis for you to implement logic gates later on whenever there is a problem in coming out with the desired output. What would be the output coming from the logic circuit itself? And so basing from the given figure is a NOT gate, there is a bubble there. Okay, it means it's a negation. So if, for example, having one variable, you only have two values there, either 0 or 1. So if you implement not 0, of course the equivalent now is 1. Not 1, the equivalent is 0. So it's pretty obvious. Not 1 is 0, not 0 is 1. Usually this is being used in the first complement. Okay, so the implementation is, for example, this is 1, so when it goes out from this gate, that is equivalent to 0. Okay, 0 is 1, 0 also is 1, 0 is 1, 1 is 0. So it's just considered as an inverter. Okay, usually we call that inverter or NOT gate. In digital systems or electronic systems, it is considered as an inverter, or the other term here is usually in electronic circuits, we call that one as a buffer. Okay, the symbol is very similar to a buffer symbol in electronic circuits. Now the next thing is we have the AND gate. AND gate, okay, if you try to take a look at the symbol, there are two inputs here, A and B, and usually it is represented by a multiplication table. So since you already have two inputs here, so the exact combination is 0 1 0 1. We have here 0 1 0 1 0 0 1 1. This one is 2 raised to 2. Okay, meaning your 2 there is the number of input variables that you have, which is A and B. So there are 2 times 2 now is, you should arrive at 4 combinations, which is equivalent to this 4 combinations of zeros and 1. So the combination is 0 0 0 1 1 0 and 1 1. So there are no other combinations aside from that. Okay, now A dot B, that is equivalent to 0. A 0 ANDed to 1 is 0, 1 ANDed to 0 is equivalent to 0, and 1 ANDed to 1 is 1 ANDed to 1 is 1. Yes, there is a proof. Okay, of course I can present that one, but of course we're going to go straight to the point, to the truth table of this AND gate. Yeah, Usually, the proving of this one is with the use of series and parallel circuits, okay, with a load. We will come to that on how are we going to prove that, so it would be a separate discussion. So 0 0 is 0, 0 1 is 0, 1 0 is 0, 1 1 is 1. The conclusion that you can get it here is that the result of an AND gate is always equivalent to 1 if both values are 1. Okay, take note of that. If both values are 1, then otherwise equivalent to 0. So any other combination aside from 1 1, the result would be, or the output is always equivalent to, so this is the output side. The output is always equivalent to 0. Alright, moving on, we have the OR gate. So the OR gate is, it has a slight difference with that of the AND gate. So if usually I tell to my class, okay, the AND gate is just like a caliber 45 bullet, okay, and then the other one here for the OR gate is just like a sniper bullet. Yes, very pointed. Okay, so here again, two variables, combination still the same, 0 1 0 1, 0 0 1 1. Okay, so the operation that is being used in what you call this one, in OR gate, is the addition sign. A while ago for the AND gate, that is a multiplication sign. Okay, so let's take a look at this one. 0 0 is equivalent to 0, 0 1 is 1, 1 0 is 1, 1 1 is 0. The conclusion that you can arrive here is that the result of the OR gate, or the output of the OR gate, is always equivalent to 0 if both inputs are 0. If both inputs are 0, then otherwise equivalent to 1. Okay, so that is just the OR gate operation. Next up, we have the NAND gate. So this is just a variation of the AND gate. So from the word alone, NAND gate, that is simply the end there means not. Okay, not AND. So whatever is the output of the AND operation, you are going to negate it. Usually, this one, the prime here, means negation. You're going to negate, and of course, prime, or sometimes there is a long over bar. So A, for example, dot B, and then there is a long over bar here, meaning you get first the AND operation and then you negate. So the bar, okay, we have here the prime, and then of course the bar is always regarded as a complement or considered as a negation. So you just negate the the AND of A dot B. So I'm going to illustrate it here. Okay, so A dot B here, if we ordinarily going to get the A dot B, 0 0 is equivalent to 0, 0 1 is equivalent to 0, 1 0 is equivalent to 0, and then 1 1 is equivalent to 1. So when you are going to implement, you're going to get the reverse of this NOT gate, of this AND operation. Definitely that would become, it's very obvious, your 0. The complement there means not, so not 0 is 1, not 0 is 1, not 0 is 1, and not 1 is equivalent to 0. So that is what we call the NAND gate. Next one is a variation also of the OR gate, so very similar, NOR gate, not OR. So notice, yeah, there's only an inclusion of bubble there. Same with that of the NAND gate. There is a bubble. Okay, and then let's verify. So taking a look at the truth table, you get first the OR operation, then you negate. So before the negation here, let's get first the OR operation. 0 0 is equivalent to 0, 0 1 is 1, 1 0 is 1, 1 1 is 1. So since there is a prime here, or a long over bar, okay, the bubble here would also mean negation. You're going to negate, or simply the correct word there is, you're going to invert, just like the inverter. Okay, so the bubble here, it means, if you try to take a look, it's just similar to a NOT gate. You're going to invert the output. So when you invert 0 1 1 1, obvious, it's now equivalent to 1 0 0 0. Okay, 1 0 0. All right, next is we have here the XOR gate, exclusive OR gate. So let's take a look at the symbol. It's just like the OR gate, but there is actually additional what you call bar here from the input side for the A and B. So this one is the distinction of the XOR gate. Since it is an OR gate, okay, the operation used here is the addition sign. If you try to take a look, there is an addition sign here, but the addition sign is actually encircled. Okay, so that is now with the use of XOR gate. Now let's take a look at the operation. Okay, so you will notice that whatever which inputs here wherein the output became 0, okay, that would be considered as the the conclusion that we can get from the XOR. If you notice 0 0, they are both equal, 1 1, they are both equal also. So the conclusion that we can arrive there is that if both inputs are the same, either 0 0 or 1 1, the output is always equivalent to 0, otherwise 1. What does it mean? If the inputs are not the same, of course, it is always equivalent to 1, otherwise 0. So the safest conclusion there is that if both inputs are the same. So an example here is that we have here 0 0, the other one is 1 1. Both A and B are 0, okay, 0 0. Both A and B is also 1 1. The output is always equivalent to 0. Okay, very obvious. Otherwise, the output is equivalent to 1. So that's what we call XOR gate. And of course, the last one is one of the expensive. Yeah. Well, these variations are very expensive already in the real the real market or in the real application. Yes, because I usually use this one when I was in the college taking up Bachelor of Science in Computer Engineering. So most of our subjects, it involves a lot of ICs, integrated circuits, and most of them are implementation of basic logic gates. So the XNOR gate is exclusive NOT OR gate. So that is only with the inclusion of N or NOT. Okay, XNOR. So whatever is the output of the XOR, you are just going to negate it. So same process with that of our NAND and NOR. So from here, let us verify without the usage of the prime here. You just get the A XOR B. 0 0 is equivalent to 0, 0 1 is 1, 1 0 is 1, and then you also have here 1 1 is still equivalent to 0. That is only the implementation of A XOR B. But since there is a bubble here, it means it is XNOR gate. Then you are just going to negate the output. So 0 becomes 1, 1 becomes 0, 1 becomes 1, and then 0 becomes 1. In the real essence, if you're going to get the the conclusion here, the output of an XNOR gate is always equivalent to 1 if both inputs are the same. Meaning both A and B 0 0, both A and B 1 1. So it's just like a negation of our XOR gate. Alright, so that ends our basic logic gates, or simply basic digital logic gates. Thank you very much.